What if I told you there's an engine so revolutionary that it achieved something engineers had been chasing for decades? 1 horsepower per cubic inch, naturally aspirated in 1957. This wasn't some exotic race engine built in limited numbers for millionaires. This was a Chevrolet, a mass-production American V8 that you could order from your local dealer. The 283 cubic inch fuel-injected V8, known as the Fuelie, didn't just break the one-to-one barrier, it shattered the entire automotive establishment's understanding of what was possible from a production engine. Picture this, it's 1957, and you're standing in a Chevrolet dealership. Elvis is on the radio. The space race hasn't started yet. Most Americans are driving cars with carburetors that haven't fundamentally changed since the 1920s. Then you spot it in the options list, Rochester mechanical fuel injection. The salesman mentions it costs $484.20 extra. That's more than many complete crate engines cost at the time. In today's money, you're looking at about $5,200 just for the fuel injection system. Your friends think you're insane. Why would anyone pay that much for something nobody understands when a 4-barrel carburetor works just fine? Here's what they didn't know. That 283 cubic inch V8 with fuel injection was about to become the most significant engine in American automotive history. Not because of its raw power, 283 horsepower sounds almost quaint today, but because it proved that American engineers could match and exceed anything coming out of Europe's most prestigious manufacturers. This was Chevrolet saying to Ferrari, Mercedes-Benz, and Jaguar, "Anything you can do, we can do in a mass-production engine that a plumber from Detroit can afford." To understand why the 283 Fuelie was revolutionary, we need to travel back to the early 1950s. General Motors was in a fight for its reputation. European sports cars were embarrassing American iron on racetracks. The Jaguar XK120 was running circles around Corvettes. Mercedes-Benz 300 SL had fuel injection and gull-wing doors that made everything from Detroit look like farm equipment. Ford was developing overhead cam engines. Chrysler had their legendary Hemi. And Chevrolet? They had the Stovebolt 6, reliable, economical, and about as exciting as watching paint dry. Enter Zora Arkus-Duntov, a Belgian-born engineer who joined Chevrolet in 1953. Duntov had raced at Le Mans. He understood European engineering. More importantly, he understood that Chevrolet needed something special to compete. When Ed Cole became Chevrolet's chief engineer in 1952, the pieces started falling into place. Cole wanted to build a new V8 from scratch, not an evolution of existing designs, something completely new. The result was the small-block Chevrolet V8, introduced in 1955 with 265 cubic inches. By 1957, it had grown to 283 cubic inches, but displacement was just the beginning. The magic number in 1957 was 1 horsepower per cubic inch from a naturally aspirated engine. Chrysler had achieved it briefly with the original Hemi in 1956, but only with dual 4-barrel carburetors, and it was temperamental. European manufacturers achieved it with tiny, high-revving engines that cost fortunes to build. Nobody had done it with a mass-production V8 that could idle in traffic, start reliably in winter, and last 100,000 miles. That was the challenge facing John Dolza, the engineer GM tasked with developing a fuel injection system for the Corvette. Here's where it gets interesting. Dolza didn't try to copy the Bosch mechanical fuel injection used by Mercedes-Benz. Instead, he developed something uniquely American, the Rochester constant flow system. Unlike modern fuel injection that pulses fuel in precise amounts, the Rochester system maintained continuous fuel flow to each cylinder through individual nozzles. A complex system of mechanical linkages, springs, and a vacuum-operated diaphragm controlled fuel delivery based on throttle position and engine vacuum. Think of it as 8 tiny fuel fountains, each precisely calibrated to deliver exactly the right amount of fuel at exactly the right time. The system was a mechanical marvel. The main fuel meter contained a vacuum-operated diaphragm that responded to manifold pressure. As you pressed the accelerator, mechanical linkage opened the throttle while simultaneously adjusting fuel flow. A high-pressure fuel pump, running at 1820 psi compared to 46 psi for carburetors, ensured consistent delivery. The fuel nozzles were positioned to spray directly at the back of each intake valve. No fuel puddling in the manifold, no distribution problems, no carburetor ice. Just precise, consistent fuel delivery to each cylinder. But fuel injection alone wouldn't achieve the magic 1-to-1 ratio. The 283 Fuelie combined multiple technologies that pushed the boundaries of 1950s production engineering. Start with the compression ratio, 10.5.1. That's aggressive even by today's standards. Most engines in 1957 ran 8.1 or 9.1 compression. Higher compression means more power from each combustion event, but it also means you need high-octane fuel to prevent detonation. The Fuelie required premium fuel, 98 octane or better. Some owners ran aviation gas when they could get it. The cylinder heads were special too. Chevrolet engineers increased valve sizes and polished the ports for better flow. Intake valves measured 1.72 inches. Exhaust valves were 1.50 inches. The combustion chambers were carefully shaped to promote turbulence and complete combustion. Every surface that air or exhaust touched was smoothed and optimized. These weren't just cleaned-up production heads, they were effectively hand-finished racing components that happened to come from the factory. The camshaft, the famous Duntov cam, was perhaps the most critical component. Duntov specified radical timing for a street engine. The intake valves opened earlier and closed later than standard. The exhaust valves stayed open longer too. This increased overlap period, when both intake and exhaust valves are open simultaneously, helped scavenge exhaust gases and pack more fresh air into the cylinders at high RPM. The trade-off was a lumpy idle that announced to everyone within a block that this wasn't your average Chevrolet. The solid lifter valve train was another racing feature. Hydraulic lifters were standard on most 283s, quiet, maintenance-free, and perfectly adequate for normal driving. But hydraulic lifters can't handle extreme RPM. They pump up with oil and hold valves open, causing catastrophic engine damage. Solid lifters required periodic adjustment, but allowed the Fuelie to rev to 6,500 RPM reliably. Some brave owners pushed them past 7,000 RPM. Remember, this was 1957. Most American V8s were done by 4,500 RPM. The bottom end was strengthened to handle the punishment. The forged steel crankshaft was balanced to tighter tolerances than standard. Connecting rods were shot-peened for strength. Pistons were forged aluminum instead of cast. The 4-bolt main bearing caps that would become legendary on later small blocks weren't used yet, but the 2-bolt mains were reinforced. Every component was selected or modified to handle sustained high RPM operation. Now let's talk about those magical 283 horsepower. On the dynamometer at the GM Tech Center in Warren, Michigan, the fuel-injected 283 consistently produced 283 horsepower at 6,200 RPM. Some engines made 285 or 286 horsepower, a few touched 290, but Chevrolet advertised 283 because it matched the displacement, 1 horsepower per cubic inch. Marketing gold. The torque figure was equally impressive, 270 pound-feet at 3,800 RPM, but those peak numbers don't tell the whole story. The Fuelie's power delivery was unlike anything from a carbureted engine. Throttle response was instantaneous, no bog, no hesitation, no flat spots. You pressed the pedal and power arrived immediately. The mechanical fuel injection eliminated the fuel starvation problems that plagued carburetors during hard cornering or acceleration. Racing drivers noticed immediately. The Fuelie could power out of corners harder and earlier than carbureted competitors. It maintained power at extreme angles that would cause carburetors to stumble. In a 1957 Corvette, the 283 Fuelie delivered devastating performance. 0 to 60 in 5.7 seconds. The quarter mile in 14.3 seconds at 95 miles per hour. Top speed, 132 miles per hour at Daytona Beach, verified by NASCAR officials. These numbers might not sound impressive today, but consider the context. A 1957 Mercedes-Benz 300 SL, costing 4 times as much, could barely match those acceleration figures. A Jaguar XK140 was slower. The Ferrari 250 GT was only marginally quicker and cost 10 times more. The Sports Car Club of America took notice immediately. In SCCA B production racing, fuel-injected Corvettes dominated. Dick Thompson, known as the Flying Dentist, won the 1957 SCCA B production championship in a Fuelie Corvette. John Fitch, Jim Jeffords, and other prominent racers campaigned fuel-injected 283s successfully. At Sebring, Daytona, and road courses across America, the distinctive mechanical whine of Rochester fuel injection became the sound of victory. But here's the kicker. Despite its performance superiority, only 1,830 fuel-injected 283s were built in 1957. Why so few? Start with that $484 price tag. The base Corvette cost $376. The fuel injection option represented a 15% price increase for about 10% more power than the dual quad carburetor setup. Many buyers couldn't justify the expense. Others were scared of the complexity. Small-town mechanics had no idea how to work on fuel injection. If something went wrong, you couldn't just rebuild it in your garage like a carburetor. The system had its quirks, too. Cold starting required a specific procedure. You had to pump the throttle exactly twice before cranking. Too little, and it wouldn't start. Too much, and you'd flood it. The high-pressure fuel pump was noisy, especially at idle. Some owners complained about a gasoline smell from the constant fuel circulation. The nozzles could clog if you used poor-quality fuel. Adjustment required special tools and knowledge that few mechanics possessed. But for those who understood what they had, the 283 Fuelie was magical. The engine ran cleaner than any carbureted equivalent. Spark plugs lasted longer. Oil stayed cleaner. There was no fuel wash in the cylinders during cold starts. Emissions, though nobody measured them carefully in 1957, were significantly lower. The precise fuel metering meant complete combustion. No rich spots, no lean spots. Just optimal air-fuel mixture in every cylinder, every time. The engineering elegance went beyond simple performance. The Rochester system included automatic mixture compensation for altitude. As you climbed into thinner air, the system leaned out the mixture automatically. Carbureted engines would run increasingly rich at altitude, losing power and efficiency. The Fuelie maintained optimal performance from sea level to mountain passes. It also compensated for temperature changes, enriching the mixture when cold and leaning it when hot. Racing development continued through 1957 and into 1958. Chevrolet engineers developed special fuel injection units with larger nozzles for competition. These racing units, identified by their 50789 casting numbers, could support over 300 horsepower with additional modifications. Racers discovered that advancing the ignition timing and running even higher octane fuel could extract another 10-15 horsepower. Some engines with special camshafts and headers produced 315 to 320 horsepower, still naturally aspirated, still 283 cubic inches. The impact on Chevrolet's reputation was immediate and lasting. Suddenly, the Bowtie brand wasn't just about affordable transportation. They had built something that could run with anything from Europe. Car and Driver magazine wrote that the fuel-injected Corvette was the first American car that could compete with the world's best sports cars on equal terms. Road and Track called it a technical tour de force. Even the European press, typically dismissive of American engineering, admitted Chevrolet had created something special. The Fuelie influenced engine development across the industry. Ford rushed to develop their own fuel injection system, though it never made production. Chrysler experimented with Bendix electronic fuel injection. Pontiac developed their own Rochester-based system. Within GM, the success of the 283 Fuelie led to continued fuel injection development. By 1963, the system had evolved to support 360 horsepower from 327 cubic inches. The 1965 396 Big Block used an evolved version, producing 425 horsepower. Let's talk about the physics that made 1 horsepower per cubic inch so significant. In 1957, extracting 1 horsepower from 1 cubic inch of displacement meant achieving exceptional volumetric efficiency. The engine had to breathe perfectly. Every cubic inch of displacement had to contribute maximum power. This required optimal cam timing, perfect fuel distribution, ideal compression, and minimal parasitic losses. It was a complete system engineering achievement, not just one breakthrough. The Rochester fuel injection system itself deserves deeper examination. The main control unit was a marvel of precision machining. Inside, a spider assembly distributed fuel to 8 lines leading to individual nozzles. The fuel meter containing the vacuum diaphragm was calibrated to deliver fuel in direct proportion to airflow. A separate enrichment circuit provided extra fuel during acceleration. The cold start circuit injected additional fuel directly into the manifold. Every function that modern electronic fuel injection performs with sensors and computers, Rochester achieved with springs, diaphragms, and precise mechanical linkages. Maintenance requirements revealed the system's complexity. Every 4,000 miles, you needed to clean the fuel filters. There were 3 of them. The nozzles required cleaning every 12,000 miles. The high-pressure fuel pump needed rebuilding every 30,000 miles. The vacuum diaphragm in the fuel meter could develop leaks. The throttle linkage required precise adjustment to synchronize with fuel delivery. It wasn't unreliable, but it demanded attention. Owners who maintained their systems properly were rewarded with exceptional performance and longevity. Those who neglected maintenance often converted back to carburetors. The cultural impact extended beyond pure performance. The 283 Fuelie became a symbol of American engineering capability during the Cold War. While the Soviets launched Sputnik in October 1957, America had produced a fuel-injected production car engine that matched anything from Europe. It was a source of national pride. Hot rodders and racers proved that American ingenuity could compete globally. The Fuelie helped establish the Corvette as a legitimate sports car, not just a boulevard cruiser with sporty styling. Production economics tell another story. Each fuel injection unit required approximately 40 man-hours to assemble and calibrate. The precision required meant high rejection rates. Many units failed final testing and required complete rebuilding. The nozzles alone cost more to manufacture than an entire 2-barrel carburetor. General Motors actually lost money on every fuel injection system sold at the $484.20 price point. They subsidized it as technology development and marketing investment. The 283 Fuelie also pioneered technologies that wouldn't become mainstream for decades. The constant flow injection principle influenced Bosch Cagetronic systems in the 1970s. The idea of individual cylinder fuel delivery predated port fuel injection by 20 years. The vacuum-based load sensing preceded mass airflow sensors. Even the high-pressure fuel system architecture became standard on modern engines. Chevrolet engineers in 1957 were solving problems the rest of the industry wouldn't encounter until emission regulations forced adoption of fuel injection in the 1980s. Racing success continued building through 1958 and 1959. Fuel-injected Corvettes won SCCA championships. They dominated production class racing. At Bonneville, fuel-injected 283s powered multiple record runs. The engine's ability to maintain power at high altitude made it perfect for Pikes Peak. Its consistent fuel delivery suited endurance racing. By 1960, the 283 Fuelie had established itself as perhaps the winningest production engine in American road racing history. But the real legacy wasn't just racing victories or technical specifications. The 283 Fuelie proved that America could innovate, not just imitate. It showed that mass production didn't mean compromising engineering excellence. It demonstrated that fuel injection was the future, even if that future took another 25 years to arrive fully. Most importantly, it established Chevrolet's small block V8 as a world-class engine architecture that continues evolving today. Consider the human element. John Dolza, who developed the Rochester system, spent 3 years perfecting it. He tested hundreds of nozzle designs. He experimented with dozens of fuel meter configurations. His team logged thousands of hours on dynamometers and test tracks. Zora-Duntov personally tested every significant modification. He drove fuel-injected Corvettes at Daytona, Pikes Peak, and the GM Proving Grounds. These engineers weren't just building an engine, they were establishing America's performance credentials. The end of production came in 1965, not because the system didn't work, but because it was too expensive and complex for mainstream adoption. By then, Chevrolet had developed the Mark IV big block engine, a 396 cubic inch big block with a simple 4-barrel carburetor, made 425 horsepower, and cost less than a fuel-injected 327. For pure power, displacement beat sophistication. The Rochester fuel injection system became a footnote, remembered only by enthusiasts and collectors. Today, an original 283 Fuelie commands extraordinary prices. A complete correct fuel injection unit sells for $15,000 to $20,000. A 1957 Corvette with factory fuel injection and documentation can exceed $200,000. The 1,830 fuel-injected engines built in 1957 have become some of the most valuable American engines ever produced. But their true value isn't monetary. The 283 Fuelie represented a philosophical statement. It said that American engineers could match anyone in sophistication. It proved that Detroit could build more than just big, lazy engines. It demonstrated that, given freedom to innovate, American automotive engineers could create world-class technology. Every modern fuel-injected engine owes something to those pioneers who achieved 1 horsepower per cubic inch in 1957. Think about what that means. In an era before computer modeling, before electronic engine management, before modern metallurgy, Chevrolet engineers created an engine that achieved a specific output comparable to modern, naturally aspirated engines. They did it with slide rules and dynamometers. They did it with mechanical fuel injection that required no electronics. They did it in a mass production engine that could be serviced by trained mechanics using hand tools. The lesson of the 283 Fuelie transcends automotive history. It reminds us that breakthrough innovation often comes from refusing to accept conventional limitations. Everyone said 1 horsepower per cubic inch was impossible in a production engine. Chevrolet proved them wrong. Everyone said fuel injection was too complex for American cars. The Rochester system, despite its quirks, proved fuel injection's superiority. Everyone said American engines couldn't compete with European sophistication. The 283 Fuelie dominated them on racetracks. Today, when we casually expect 100 horsepower per liter from ordinary engines, it's easy to forget how revolutionary the 283 Fuelie was. But in 1957, achieving 283 horsepower from 283 cubic inches without supercharging, turbocharging, or exotic materials was like breaking the sound barrier. It was a number that seemed impossible until someone did it. And once Chevrolet proved it possible, the entire industry had to catch up. The 283 Fuelie didn't just shock everyone by achieving 1 horsepower per cubic inch. It shocked them by doing it in a Chevrolet. It shocked them by being reliable enough for daily driving. It shocked them by costing less than many thought possible. Most of all, it shocked them by proving that American engineering could lead, not just follow. That might be the greatest achievement of all. What's the most impressive engine specification you've ever encountered? Drop a comment below and let's discuss what makes certain engines truly legendary. And if you enjoyed this deep dive into one of America's most significant engines, make sure to subscribe, because we're just getting started exploring the machines that changed history.